a natural object like a comet or an asteroid, and 10 is a definitely technological object that maneuvers, broadcasts a signal, or transmits some artificial light.
In the vast expanse of the cosmos, two comets stand apart, one born from the depths of our own solar system, the other an ancient traveler from interstellar space. Both are illuminated by the sun's distant glow, yet their stories could not be more different. 1. C2025 R2 SWAN is a fragile, disintegrating wanderer, its icy heart crumbling as it draws near to the sun. The other, 3I Atlas, is a mysterious interstellar voyager, speeding through the inner solar system with a path that suggests it has traveled for billions of years. Together, they offer a rare opportunity to witness the extremes of cometary behavior, revealing the dynamic nature of our cosmic neighborhood and the enigmatic origins of objects beyond our system. Comets have long fascinated astronomers and stargazers alike, not only for their ethereal beauty, but for the secrets they carry. They are cosmic time capsules, remnants of the early solar system, and possibly even older, containing materials that predate our own star. Their journeys through space tell us about the forces that shape planetary systems, the evolution of celestial bodies, and the potential for life beyond Earth. Yet, despite centuries of observation, comets still hold many mysteries. Why does one comet disintegrate while another survives its passage near the sun? What can we learn from the differences in their compositions and trajectories? These are the questions that drive our exploration of C2025 R2 SWAN and 3I Atlas. At the heart of this cosmic contrast lies the fundamental difference between a native solar system comet and an interstellar interloper. C2025 R2 SWAN was discovered in late March 2025, its existence revealed through the Solar and Heliospheric Observatory's SWAN instrument. Initially expected to become a bright spectacle visible to the naked eye, the comet instead exhibited signs of disintegration, its nucleus breaking apart as it neared the sun. In stark contrast, 3I Atlas, discovered in July 2025, is an interstellar object with an incredibly high velocity, suggesting it originates from a distant star system. Its path is so fast and so far from being influenced by the sun's gravity that it will eventually escape the solar system entirely. These two comets represent the extremes of cometary behavior, one a fleeting visitor from the outer reaches of our system, the other a relic from another corner of the galaxy. This unique juxtaposition presents a remarkable opportunity to explore the science of comets in unprecedented ways. By studying C2025 R2 SWAN, scientists can gain insights into the processes that lead to cometary disintegration, shedding light on the volatile nature of these icy bodies. Meanwhile, 3I Atlas offers a glimpse into the composition of interstellar objects, potentially revealing materials that have never been exposed to the conditions of our solar system. Together, they form a cosmic puzzle, one piece of which may help us understand the origins of life itself. As we embark on this journey through the lives of these two comets, we will uncover the science behind their differences, the mysteries they embody, and the profound implications they hold for our understanding of the universe. To truly grasp the significance of C2025 R2 SWAN and 3I Atlas, we must first understand their origins and the paths they have taken through the cosmos. Each comet tells a unique story, shaped by the forces of gravity, solar radiation, and the vast distances of space. C2025 R2 SWAN emerged from the depths of our own solar system, its journey beginning in the distant Kuiper Belt, a region teeming with icy remnants left over from the formation of the planets. In contrast, 3I Atlas hails from interstellar space, a rare visitor that has traveled for billions of years before crossing our cosmic doorstep. C2025 R2 SWAN was first observed in late March 2025 through images captured by the Solar and Heliospheric Observatory's SWAN instrument. This instrument, designed to map the distribution of hydrogen atoms in the solar wind, inadvertently revealed the presence of a cometary object. At the time of its discovery, the comet was located approximately 1.62 astronomical units (AU), the average distance between Earth and the Sun, from our planet, and 0.92 AU from the Sun itself. Based on its trajectory, Astronomers determined that C2025R2 SWAN followed an elliptical orbit with a nearly parabolic shape, indicating that it had spent the majority of its existence in the far reaches of the solar system before being perturbed by gravitational forces and sent toward the inner planets. The comet's journey brought it ever closer to the Sun. With its perihelion, the point in its orbit where it is nearest to the Sun, occurring on September 12, 2025, at a distance of 0.5 AU. As it approached the Sun, C2025R2 SWAN experienced intense heating, causing its icy nucleus to sublimate and release gases and dust into space. This process created a glowing coma, the gaseous envelope surrounding the nucleus, and a long luminous tail that stretched across the sky. However, unlike many comets that maintain structural integrity during their solar encounter, C2025R2 SWAN showed signs of instability. By mid-April 2025, observations revealed that the comet had begun to disintegrate, its nucleus breaking apart and leaving behind a cloud of debris. This disintegration was not entirely unexpected. Many comets, particularly those making their first approach to the inner solar system, lack the structural strength to withstand the extreme conditions near the Sun. As the nucleus heats up, volatile compounds such as water ice, carbon dioxide, and methane rapidly sublimate, creating internal pressure that can cause fractures and fragmentation. In the case of C2025R2 SWAN, this process was accelerated, and by early May 2025 the comet had largely vanished from view, its remnants scattering into space. Despite its brief and dramatic end, the comet provided valuable insights into the fragility of cometary structures and the forces that govern their evolution. While C2025R2 SWAN was a fleeting guest from the outer solar system, 3I Atlas represents something far more extraordinary, an interstellar object with origins beyond our own planetary system. Discovered in July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas Telescope in Chile, 3I Atlas was immediately identified as an interstellar visitor due to its hyperbolic trajectory and extreme velocity. Unlike the nearly parabolic orbit of C2025R2 SWAN, 3I Atlas followed a highly eccentric path with an orbital eccentricity of 6.141, indicating that it was not gravitationally bound to the Sun and would ultimately escape the solar system. The comet's arrival marked a significant milestone in astronomy. Prior to 3I Atlas, only two interstellar objects had been definitively identified, 1I Oumuamua in 2017 and 2I Borisov in 2019. The discovery of 3I Atlas confirmed that interstellar objects are not rare anomalies, but rather a natural component of the galactic environment. More importantly, it offered an unprecedented opportunity to study the composition and behavior of an object that had formed in a different star system, providing a glimpse into the diversity of planetary materials across the Milky Way. As 3I Atlas approached the Sun, it displayed characteristics similar to those of native comets. Its nucleus, estimated to be between 0.32 and 5.6 kilometers in diameter, released gases and dust as it was heated by solar radiation, forming a coma and a distinct tail. Observations conducted by the James Webb Space Telescope (JWST) and the Hubble Space Telescope revealed that 3I Atlas was unusually rich in carbon dioxide and contained trace amounts of water ice, water vapor, carbon monoxide, and carbonyl sulfide. These findings suggested that the comet's chemical makeup differed from that of typical solar system comets, hinting at a unique origin or evolutionary history. Perhaps the most intriguing aspect of 3I Atlas is its potential age. Based on its trajectory and velocity components, astronomers estimated that the comet could be between 3 and 14 billion years old, far older than the 4.6 billion-year-old solar system. If accurate, this would mean that 3I Atlas predates our own planetary system, carrying with it the chemical signatures of an era when the Milky Way was much younger. Such an object serves as a cosmic messenger, offering a direct sample of the conditions that existed in a different part of the galaxy, long before the birth of Earth. The stark differences between C2025R2 SWAN and 3I Atlas highlight the diverse nature of cometary bodies and the vast range of environments in which they originate. While C2025 R2 SWAN was a fragile, short-lived visitor from the outer solar system, 3I Atlas was a resilient interstellar traveler that had endured the immense journey across interstellar space. The fate of C2025 R2 SWAN, its disintegration as it approached the Sun, demonstrated the vulnerability of cometary structures to solar radiation and gravitational forces, whereas the survival of 3I Atlas suggested that some interstellar objects possess the resilience to withstand the challenges of traversing multiple star systems. These two comets also serve as reminders of the dynamic nature of our cosmic neighborhood. The discovery of interstellar objects like 3I Atlas challenges our understanding of planetary formation and the prevalence of cometary bodies in the galaxy. Meanwhile, the study of comets like C2025 R2 SWAN provides insight into the processes that shape the evolution of solar system objects. Together, they offer a compelling narrative of cosmic exploration, revealing the interconnectedness of planetary systems and the enduring mysteries of the universe. To appreciate the 100x brightness disparity between C2025 R2 SWAN and 3I Atlas, we must delve into the intricate mechanisms that govern cometary luminosity. At first glance, the brightness of a comet might seem to depend solely on its distance from the Sun and the size of its nucleus. However, the reality is far more nuanced, involving a delicate interplay of factors such as composition, sublimation rates, and the efficiency of dust and gas emission. These elements determine how effectively a comet reflects sunlight and emits its own light, ultimately shaping its visibility from Earth. The composition of a comet's nucleus plays a pivotal role in its brightness. Comets are often referred to as dirty snowballs, a description that captures their mix of volatile ices, such as water, carbon dioxide, and methane, embedded in a matrix of rocky and organic materials. When a comet approaches the Sun, the ices sublimate, releasing gases and entrained dust into space to form the coma and tail. The specific types and quantities of these volatiles influence the comet's activity level, and consequently, its brightness. C2025 R2 SWAN, for instance, exhibited signs of rapid sublimation as it neared the Sun, but its disintegration likely reduced the efficiency of gas and dust emission. The breakup of its nucleus fragmented the comet into smaller particles, which may have scattered the emitted material rather than concentrating it into a cohesive coma. This dispersion could have diminished the comet's ability to reflect sunlight, contributing to its dimming despite its proximity to the Sun. In contrast, 3I Atlas demonstrated a more stable and sustained emission profile. Observations by the James Webb Space Telescope (JWST) revealed that 3I Atlas is unusually rich in carbon dioxide, a volatile with a lower sublimation temperature than water ice. This characteristic allows the comet to remain active at greater distances from the Sun, maintaining a steady supply of gas and dust to fuel its coma. Additionally, the presence of water ice, water vapor, and other compounds in 3I Atlas's coma suggests a balanced emission of both gas and dust, optimizing its reflectivity and enhancing its visibility. The chemical composition of a comet also affects the color of its coma and tail, which can influence perceived brightness. For example, the presence of carbon-based molecules in 3I Atlas's coma imparts a reddish hue, a feature associated with dust-rich comet. This dust component scatters sunlight efficiently, amplifying the comet's luminosity. Conversely, C2025 R2 SWAN may have lacked a comparable dust-to-gas ratio, resulting in a less reflective coma and a dimmer appearance. Sublimation, the process by which ices transition directly from a solid to a gas, is the primary driver of cometary activity. The rate at which a comet sublimates its ices determines the volume of gas and dust expelled into space, which in turn shapes the size and density of the coma. Higher sublimation rates typically correlate with greater brightness. As more material is available to reflect and scatter sunlight, the sublimation rates of C2025 R2 SWAN and 3I Atlas were influenced by their respective distances from the Sun and the composition of their nuclei. C2025 R2 SWAN reached a perihelion of 0.5 AU, placing it within the inner solar system where temperatures are high enough to accelerate sublimation. However, The comet's disintegration likely disrupted the continuity of its nucleus, reducing the efficiency of sublimation and limiting the production of gas and dust. The fragmentation of its nucleus may have also exposed deeper layers of volatile ices, leading to sudden bursts of activity followed by rapid dimming as these resources were depleted. In contrast, 3I Atlas's perihelion of 1.36 AU placed it in a cooler region of the inner solar system, where sublimation proceeds at a more gradual pace. This slower rate allowed the comet to maintain a steady flow of gas and dust over an extended period, sustaining a consistently bright coma and tail. The presence of carbon dioxide in 3I Atlas's nucleus further contributed to its prolonged activity, as this compound sublimates at a lower temperature than water ice, enabling the comet to remain active even as it moves farther from the Sun. The efficiency of sublimation is also affected by the physical properties of a comet's surface. Amper's rough or porous surface can trap heat and insulate the underlying ices, slowing the sublimation process. Conversely, a smooth or compacted surface may allow for more rapid sublimation. While the exact surface characteristics of C2025 R2 SWAN and 3I Atlas remain uncertain, the stability of 3I Atlas's emission profile suggests that its surface may have retained sufficient insulation to regulate sublimation and prolong its activity. The brightness of a comet is determined by the combined effects of reflected sunlight from its dust and the intrinsic glow of its gas emissions. Dust particles, which can range in size from microns to millimeters, are highly effective at scattering sunlight, producing the brilliant diffuse coma and tail that make comets so visually striking. Gas emissions, on the other hand, contribute to the comet's luminosity through fluorescence and ionization, processes that emit light at specific wavelengths. C2025 R2 SWAN likely suffered from a diminished dust-to-gas ratio as a result of its disintegration. The fragmentation of its nucleus may have dispersed the dust into a less concentrated cloud, reducing its ability to reflect sunlight. Additionally, the comet's rapid dimming suggests that its gas emissions were insufficient to sustain a bright coma, further diminishing its visibility. In contrast, 3I Atlas exhibited a robust combination of dust and gas emissions. Observations by the Very Large Telescope, VLT, and JWST revealed the presence of cyanide gas and atomic nickel vapor in the comet's coma, substances that fluoresce under sunlight and contribute to its overall brightness. The red hue of 3I Atlas's coma, attributed to dust particles, indicates a high dust-to-gas ratio, which enhances its reflectivity and ensures a steady supply of material to sustain its luminosity. The efficiency of dust and gas emission is also influenced by the comet's velocity relative to the Sun. As a comet approaches perihelion, the increased solar radiation accelerates the ejection of material, creating a more dynamic and luminous coma. However, the high velocity of 3I Atlas, moving at 68 kilometers per second at perihelion, may have limited the extent of its interaction with the solar wind, preserving the integrity of its coma and tail. This stability likely contributed to the comet's sustained brightness, whereas the disintegration of C2025 R2 SWAN may have disrupted the coherence of its emissions, leading to a rapid decline in visibility. The 100x brightness disparity between C2025 R2 SWAN and 3I Atlas underscores the complexity of cometary behavior and the factors that govern their visibility. While both comets rely on sublimation and emission to produce their luminosity, their differing compositions, trajectories, and structural integrity have resulted in vastly different outcomes. C2025 R2 SWAN, a fragile native of the solar system, succumbed to the stresses of its solar encounter, its disintegration limiting its ability to sustain a bright coma and tail. In contrast, 3I Atlas, an ancient interstellar traveler, has maintained its structural integrity and activity, allowing it to remain a prominent presence in the night sky. These contrasting fates highlight the importance of understanding the dynamic interplay between a comet's physical properties and its environment. By studying comets like C2025 R2 SWAN and 3I Atlas, scientists can refine their models of cometary evolution gaining insights into the processes that shape these celestial wanderers and their roles in the broader context of the solar system and beyond. The study of comets like C2025 R2 SWAN and 3I Atlas extends far beyond their individual characteristics. It opens a window into the broader mysteries of the universe. These celestial bodies are not merely transient phenomena, but cosmic messengers that carry clues about the formation of planetary systems, the origins of life, and the distribution of matter across the galaxy. By analyzing their behavior, composition, and trajectories, scientists can piece together the history of our solar system and gain insights into the vast, interconnected web of stellar systems that populate the cosmos. One of the most profound implications of cometary study lies in its connection to the origins of life. Comets are believed to have played a crucial role in delivering essential organic compounds and water to the early Earth, setting the stage for the emergence of life. The presence of complex organic molecules in comets such as 3I Atlas suggests that the building blocks of life may be more widespread in the universe than previously thought. The James Webb Space Telescope's observations of 3I Atlas, for instance, revealed the presence of carbon dioxide, water ice, and other volatile compounds, all of which are integral to prebiotic chemistry. If these materials are common among interstellar comets, it implies that the seeds of life may have been seeded on other planets across the galaxy, raising the tantalizing possibility that life could exist elsewhere. Moreover, the study of comets like C2025 R2 SWAN and 3I Atlas contributes to our understanding of the solar system's formation and evolution. Comets are remnants of the primordial material that coalesced to form planets, and their compositions reflect the conditions of the early solar system. By analyzing the isotopic ratios and chemical makeup of cometary material, scientists can reconstruct the processes that shaped the solar system's architecture. For example, the disintegration of C2025 R2 SWAN provides valuable data on how cometary nuclei respond to solar radiation and gravitational forces, helping to refine models of cometary evolution. Similarly, the unusual composition of 3I Atlas, with its high concentration of carbon dioxide and other exotic compounds, challenges existing theories about the uniformity of planetary materials and suggests that interstellar comets may originate from diverse stellar environments. The discovery of interstellar comets like 3I Atlas also raises fundamental questions about the nature of the Milky Way and the frequency of such objects. Prior to 3I Atlas, only two interstellar objects, 1I Oumuamua and 2I Borisov, had been confirmed as visitors from other star systems. The identification of 3I Atlas as a third interstellar comet indicates that these objects may be more common than previously assumed, implying that the galaxy is a dynamic exchange of material between planetary systems. This realization has profound implications for our understanding of the distribution of matter in the universe and the likelihood of encountering interstellar objects in the future. Furthermore, the study of comets contributes to the broader field of astrobiology by addressing the question of whether life's ingredients are universal. The presence of organic molecules in comets supports the hypothesis that the precursors to life are not unique to Earth, but may be abundant in the cosmos. This perspective aligns with the panspermia theory, which posits that life could have been transported between planets via comets and asteroids. While this idea remains speculative, the discovery of complex organic molecules in comets like 3I Atlas strengthens the argument that the building blocks of life are widespread, potentially seeding other worlds with the necessary ingredients for biological processes. In addition to their role in the search for extraterrestrial life, comets also provide critical insights into the physical processes that govern the universe. The study of their trajectories and interactions with the solar wind helps scientists understand the dynamics of the solar system's outer regions and the forces that influence the movement of celestial bodies. For example, the hyperbolic trajectory of 3I Atlas, with an orbital eccentricity of 6.141, demonstrates the immense velocities at which interstellar objects travel. This information is invaluable for refining models of gravitational interactions and improving our ability to predict the paths of future interstellar visitors. The study of comets also has practical applications in planetary defense. While neither C2025 R2 SWAN nor 3I Atlas posed a threat to Earth, the observation of cometary behavior informs strategies for mitigating potential impacts from near-Earth objects. By understanding how comets disintegrate under solar radiation and gravitational forces, scientists can develop more accurate models for predicting the trajectories and stability of potentially hazardous objects. This knowledge is essential for developing early warning systems and response protocols to protect our planet from future impact events. Perhaps the most profound implication of cometary study is its ability to inspire a sense of wonder and curiosity about our place in the universe. The fleeting beauty of a comet's passage through the night sky reminds us of the vast, interconnected nature of the cosmos and the shared history of all celestial bodies. The discovery of interstellar comets like 3I Atlas underscores the idea that the universe is not a static, isolated entity, but a dynamic, ever-evolving tapestry of matter and energy. By studying these cosmic travelers, we not only expand our scientific knowledge, but also deepen our appreciation for the mysteries that lie beyond our own planetary system. As technology advances, the study of comets will continue to yield new insights into the universe. Future missions, such as the proposed Europa Clipper and the James Webb Space Telescope's deep space observations, will enable scientists to probe the composition of comets in greater detail, uncovering secrets that have remained hidden for millennia. These efforts will not only enhance our understanding of comets, but also contribute to broader scientific inquiries into the origins of life, the structure of the universe, and the potential for human exploration beyond our solar system. In the grand tapestry of the cosmos, comets like C2025 R2 SWAN and 3I Atlas serve as reminders of the universe's complexity and the enduring mysteries that await discovery. Their contrasting fates, one a fragile, disintegrating wanderer from the outer solar system, the other a resilient interstellar traveler, highlight the diversity of celestial bodies and the dynamic processes that shape their evolution. As we continue to study these cosmic messengers, we inch closer to unraveling the fundamental questions that define our existence and our place in the universe. As we draw this cosmic journey to a close, the stories of C2025 R2 SWAN and 3I Atlas remind us of the vast, interconnected nature of the universe. These two comets, though vastly different in their origins and fates, share a common thread. They are both transient visitors to our night sky, each carrying with them the echoes of distant histories and the promise of future revelations. In their fleeting brilliance, they illuminate not only the mysteries of their own existence, but also the broader narrative of our place within the cosmos. The disintegration of C2025 R2 SWAN serves as a poignant reminder of the impermanence of celestial phenomena, like a fragile snowflake melting in the sun. This comet's journey ended in a cascade of dust and gas, a final act of transformation that left behind a trail of scientific inquiry. Yet, even in its demise, C2025 R2 SWAN imparted invaluable lessons about the volatile nature of comets and the delicate balance of forces that govern their evolution. Its story, though brief, underscores the dynamic and ever-changing character of the universe, where creation and destruction are intertwined in an eternal cycle. In contrast, the resilience of 3I Atlas speaks to the enduring legacy of interstellar travelers. This ancient comet, forged in the crucible of a distant star system, has traversed the vast emptiness of space for billions of years. Its arrival in our solar system is a testament to the interconnectedness of the Milky Way, a reminder that the boundaries between planetary systems are not as rigid as they may seem. As 3I Atlas continues its journey outward, it carries with it the chemical signatures of a different corner of the galaxy, offering a rare glimpse into the diversity of materials that shape the cosmos. In its quiet persistence, 3I Atlas embodies the spirit of exploration, reminding us that the universe is a vast, uncharted frontier waiting to be explored. Together, these comets challenge us to rethink our understanding of the universe and our place within it. The study of comets like C2025 R2 SWAN and 3I Atlas has expanded our knowledge of planetary formation, the origins of life, and the distribution of matter across the galaxy. These celestial wanderers are not mere curiosities, but vital pieces of a larger puzzle, each contributing to the collective effort to unravel the mysteries of the cosmos. They remind us that the universe is not a static, isolated entity, but a dynamic, evolving tapestry of matter and energy, where every object, no matter how small, plays a role in the grand narrative of existence. As we gaze upward at the night sky, we are reminded that we too are part of this cosmic story. The same elements that compose comets, the water, carbon, and other volatile compounds are present in our own bodies, a testament to the shared heritage of all matter in the universe. The light that illuminates the comet's tails is the same light that once shone on the early Earth, nurturing the conditions for life to emerge. In this profound connection, we find a sense of unity with the cosmos, a recognition that our existence is deeply intertwined with the stars above. The mysteries of the universe are vast, and the study of comets like C2025R2, SW-SWAN, and 3I Atlas is but one thread in the intricate fabric of cosmic exploration. As technology advances and our understanding deepens, we will undoubtedly uncover new questions and new wonders, each one expanding the boundaries of our knowledge. The journey of these comets, from the depths of the solar system to the far reaches of interstellar space, mirrors our own quest for understanding. A journey driven by curiosity, guided by science, and illuminated by the endless possibilities of the cosmos. In the end, the stories of C2025R2 SWAN and 3I Atlas are not just tales of celestial bodies, but reflections of our own human experience. They remind us of the fleeting beauty of existence, the resilience of the unknown, and the boundless potential of discovery. As we continue to explore the universe, may we carry forward the same sense of wonder that these comets inspire, ever eager to uncover the next chapter in the story of the cosmos.